Good morning everyone. I Aditya from BSc Chemistry on the second year is today here to make a video on the chapter phenols for the visually impaired students. Let's start with the introduction. Phenols are the aromatic hydroxy compound in which the hydroxyl group is directly attached to an aromatic ring. They may be represented by the general formula AROH, where AR represent a phenyl, a substituted phenyl, or some other aryl group such as naphthyl. Depending upon the number of hydroxyl groups attached to the aromatic rings, the phenols may be classified as mono, di, trihydric phenols and so on. For example, we have phenol, ocresol, risorcresol, pyrogallol. The hydroxyl group attached to the aromatic ring is known as phenolic group. As already stated in the chapter 3, phenols are different from the aromatic hydroxy compounds in which the hydroxyl group is present in the side chain. The latter type of compounds are in fact aryl substituted aliphatic alcohols, and their behavior is similar to of aliphatic alcohols. However, both phenols and aromatic alcohols resemble each other in undergoing the electrophilic aromatic substitution and in certain respects. Nomenclature of the phenols. The simplest member of phenols is always known by its popular name phenol, although its IUPAC name is benzonal. All substituted monohydric phenols are named as derivative of the simplest members of the series, that is phenol. However, methyl phenols possesses the special common names. The positions of the substituents with respect to the OH groups are denoted by OMP. It means ortho, meta and para in the common system, but by numbers in IUPAC system with the OH groups carrying the number 1. The following examples illustrate the method of naming phenols. The name given in brackets are the common names. Here they are: phenols, orthochlorophenol 2,4-dinitrophenol, 3-methylphenol, 3-methylphenol, orthometa and paracresols. The di-triphenols have the IUPAC's name benzodiols and benzotriols respective to each other, but most of them are known by their special names as given below, that is catechol, resorcinol, hydroquinone or piquinol, pyragallol, chloroglucone. It should be noted that, however, that when a compound has some functional group such as carboxyl group, ester or carbonic group in addition to the phenolic group, the compound is named as hydroxy derivative of the acid ester or the carbonyl compound. For example, 4-hydroxybenzaldehyde. Structure and bonding. Phenols are the compounds having the hydroxyl group directly bonded to the benzene ring, while oxygen hydroxyl group is in sp3 hybridized state. The carbon of the benzene ring to which the oxygen is bonded in the sp2 hybridized state. Resonance interaction takes place between a lone pair of electrons on oxygen and on the benzene ring, so that the phenol exists as a resonance hybrid of the resonating structure as shown below. It consists of 5 resonating structures. Due to resonance, the carbon-oxygen bond acquires some double bond character and becomes shorter and shorter than the carbon-oxygen bond in alcohols. At the same time, oxygen requires a slight positive charge, due to which it attracts the electron pair of OH bond strongly towards itself. As a result, the OH bond in phenols become more polar than in alcohols. Due to the above structural features, phenols behave directly from alcohols in many respects and are treated as a separate class of compounds. Methods of formation. First one is hydrolysis of diazonium salts. This is probably the most convenient method of preparation of phenols. This reaction is carried out by slowly adding the diazonium salt to the excess of to boil the dilute sulfuric acid. Second method is alkali fusion of sulfonates. In this method, phenols are obtained by the fusion of the sodium salts of aromatic sulfonic acids with sodium hydroxide, followed by the acidification. This method cannot be applied to the salts of sulfonic acids contain substituents such as chlorine, nitroxide, and COH due to the possibility of various side chain reactions. The third method is from isopropyl benzene or cumene. This method is particularly used for the large scale production of phenol from isopropyl benzene, popularly known as cumene. The fourth method is from the aryl halides. Substituted phenols having the electron withdrawing groups like nitrogen oxide group in its ortho and para positions to the OH group can be easily prepared from the corresponding aryl halides by treatment with the aqueous sodium hydroxide. Phenol itself is manufactured by the heating of chlorobenzene with a 10% of hydroxide solution at a temperature of 623 Kelvin under the pressure of 200 atmosphere in the presence of copper salt. This process is known as Dawes process. The fifth method of preparation is the from the phenolic acids. Distillation of sodium salt of phenolic acids with soda lime yields phenol. From the Grignard reagents, we can also made the phenol by treating it with aryl magnesium bromide with oxygen followed by the hydrolysis of the product. The seventh method is the from coal tar. Phenols and creosotes are obtained on a large scale from the middle oil fraction obtained on distillation of coal tar. Physical properties of phenol. Physical state. Pure phenols are generally colorless liquids or solids, but they usually slightly colored as they readily oxidized even in air, and the oxidation products are colored compounds. At the same time, the substituents like NO2 impart color to phenols. Boiling points. Due to the formation of the intermolecular hydrogen bonding, phenols are considerably higher than the corresponding hydrocarbons and aryl halides which do not contain any hydrogen bonds. Third one is solubility. Phenols are particularly practically insoluble in water, although phenol itself and some di and trihydric phenols are fairly soluble. The solubility is of these compounds is probably due to the formation of hydrogen bonds with water. But the extent of hydrogen bond formation is very small due to the large size of phenyl group, which masks the polar character of the OH bond. All phenols are soluble in aqueous alkaline solutions due to the formation of water soluble salts. Chemical properties. Phenols are highly reactive compounds which combine the reactions of both the hydroxyl group and the aromatic rings. The important reactions of phenols are discussed below. First is reactions of phenolic group acidity. Phenols are weakly acidic compounds. They react with aqueous alkali metal hydroxides to form the salts known as phenoxides. However, phenols do not react with aqueous carbonates or bicarbonates. Moreover, the salts are converted into the phenols by the mineral acids or carboxylic acid or even the carbonic acid. These observations indicate that phenols are very weak acids, weaker than the carboxylic acid or even to the carbonic acid. This is confirmed by the comparison of their acidity constant, that is Ka or pKa values, while phenols having the K values of the order 1 and 1 angstrom, carbolic acid and carbonic acid having the values of 1 into 10 to the power minus 5 and minus 7 respectively. Even though very weakly acid themselves, phenols are much acidic than alcohols which have high Ka values of the order of 1 into 10 to the power minus 16 to 1 into 10 to the power minus 18. This appears to be rather surprising since both phenols and alcohols are characterized by the presence of hydroxyl groups. What then is the reason that an OH attached to an aromatic ring is so much acidic than the OH attached to an alkyl group? We would attempt to answer this question by considering the stability of the ions formed relative to the stability of unionized compound. Explanation of acidic character of phenol. The ionization of phenols is an equilibrium reaction involving the ionized phenol and phenoxide and hydronium ions, as for example, now either phenol nor phenoxide ion can be represented by only one valence bond formula. On the other hand, each of them is a reasonable resonance hybrid of various contributing structures as shown. It may be noted that the contributing structures, that is 1C, 1D and 1E of phenol, involve the separation of the charge and are therefore less stable than the structures of 1A and 1B. On the other hand, in the case of phenoxide ion, none of the contributing structures involve a charge separation and the structures are equally stable. As such, phenoxide ion is resonance stabilized to a greater extent than phenol. Therefore, the equilibrium between the phenol and phenoxide favors the formation of phenoxide ion and the hydronium ion, that is. The comparison with alcohols. In case of alcohols, the equilibrium reaction involving alcohol and alkoxide ion does not favor the formation of alkoxide ion and hydronium ion. This is because there is no resonance stabilization of alkoxide ion relative to the alcohol, since neither the alcohol nor the alkoxide exhibit the resonance. Hence, it should not be surprising that compared to alcohols, phenols ionize more readily to form the phenoxide ion and hydronium ion. In other words, phenols are more acidic than the alcohols. Effects of substituents on the acidity of phenols. The acidity of phenols is strongly influenced by the substituents attached to the benzene ring and their position. This is because of the equilibrium in the reaction between phenol and water to furnish the phenoxide ion and hydronium ion depends upon the stability of the products relative to the stability of reactants. Any factor which stabilizes the phenoxide ion more than the parent phenol should increase the acidity without any factor that stabilizes the phenoxide ion should decrease the acidity as illustrated below. Nature of the substituents on benzene ring. Electron withdrawing substituents. Phenols having the electron withdrawing substituents such as halogens and nitro group are more acidic than the phenol itself. This is because an electron withdrawing substituent, say G, attracts the electron towards itself and thus disperses the negative charge of the phenoxide ion. As a result, it stabilizes the phenoxide ion and increases the acidity of phenol. Electron releasing substituents. Phenols containing electron releasing groups such as alkyl groups are less acidic than the phenol itself. This is because an electron releasing the substituent, say G, releases the electrons away from itself and thus intensify the negative charge on the phenoxide ion. In this way, it destabilizes the anion and thereby decreases the acidity of phenol. In short, electron withdrawing groups increase the acidity of phenol while electron releasing groups decreases their acidity. Remember that lower the pKa value, higher the acidity. Position of the substituents relative to the hydroxyl group. Apart from the nature of the substituent, the position of the substituent relative to the hydroxyl group also has a large number influence on the acidity of phenol. This may be explained as below. The stabilizing or destabilizing influence of the substituents operates through the inductive effect as well as the resonance effect. The intensity of the inductive effect of the substituent decreases as the distance from OH group increases. Ortho, then meta, then para. This is why acidity of chlorophenols. Third one is the resonance effect is now pronounced by if the substituent is in ortho or para position than in meta position. To understand this, let us examine the contribution of ortho, meta and para nitrophenoxide ions. It may be seen that each of ortho and para nitrophenoxide ion is a resonance hybrid of 5 contribution structures. In one of the structures in each case, the conjugation is extended up to oxygen atom of nitrogen group, but no such conjugation is possible for the meta nitrophenoxide ion and has only 4 contributing structures. The net result is that there is a greater resonance stabilization of ortho and para anions than the M isomer. As such, ortho and para-nitrophenols are much stronger acids than the metonitrophenol. Second factor is ether formation, that is the Williamson synthesis. On reaction with the alkyl halides or dialkyl sulfates in alkaline medium, phenols are converted into the corresponding alkyl ethers. The alkyl halide or the sulfates undergoes nucleophilic substitution by the phenoxide ion present in the alkyl solution of phenol. Thus we have the di-alkyl sulfate is converted into ethers and alkyl sulfate ion. This is an interesting rearrangement reaction involving the aryl-allyl ethers. Claisen rearrangement. When heated to 475 degree, the allyl group of the ethers migrates from ether oxygen to the ring carbon at the ortho position. If both the ortho positions are already occupied, the allyl groups migrates to the para position. Mechanism of ortho rearrangement. Ortho isomerization involves a concerted mechanism in which the cleavage of the allyl oxygen bond is synchronized with the formation of allyl carbon bond at the ortho position. The cyclohexadienone intermediate thus formed undergoes a tautometric change to give the ortho-allyl phenol in which the rings regains the aromatic character as depicted below. It may be carefully noted that the gamma carbon of the allyl group with respect to oxygen which attaches itself to the ring carbon. This is supported by the fact that orthomigration involves an inversion in the position of the substituents in the allyl groups with respect to that of the starting compound. For example, mechanism of the para rearrangement. Para isomerization involves two stages. In first stage, the orthomigration takes place and the cyclohexadienone intermediate is formed, but this intermediate cannot undergo the tautomerization since there is no hydrogen at the ortho positions. As such, this intermediate undergo another migration of the allyl group, ultimately yield the final product. It may be noted that in the para isomerization, two migration can take place, of which accompanied by the inversion. In other words, our inversion is followed by another inversion, so that there is no net inversion in the position of the substituents with respect to the starting compound. Third is ester formation, that is acylation. Like alcohols, phenols are converted into esters by the reaction with carboxylic acids, acid chloride or anhydrides. However, in actual practice, esterification is better carried out by the use of acid chlorides or anhydrides in the presence of an either of an acid or a base as a pyridine, such as pyridine. Benzolization of phenol is usually carried out in the presence of aqueous NaOH since benzoyl chloride is not easily hydrolyzed by the alkalis. This reaction is called Schotten-Bowman reaction. Mechanism: to start with, the alkali attacks the phenol to form the phenoxide ion. This anion undergoes nucleophilic attack on the carbonyl carbon of the acid to form a tetrahedral intermediate. This intermediate then loses a chloride ion to form the ester. Fries rearrangement. If an ester of a phenol is heated with the aluminum chloride, the acyl group migrates from the phenolic oxygen to the ortho or para position on the ring. This is called Fries rearrangement. For example, At low temperature, para product predominates, while at high temperature, orthoisomers is the main product. Mechanism: the rearrangement probably involves the formation of acylium ion, which then attacks the aromatic ring, as in Friedel-Crafts acylation. This complete mechanism may be summed up as follows. Reaction with the zinc dust. When distilled zinc dust, phenols form corresponding hydrocarbons, that is, benzene formed with phenol. Reaction with ammonia. When heated with the ammonia at high temperature and pressure in the presence of catalysts like anhydrous zinc chloride, OH group of phenols is replaced by the amide group. Reaction of aromatic ring, that is electrophilic substitution. Phenols readily undergo electrophilic aromatic substitution reactions. The OH group linked to an aromatic ring activates the ring to an electrophilic substitution and directs the incoming group to ortho and para position. In fact, the OH group is a very powerful activator, and unless precautions are taken, polysubstitution takes place. Explanation of ortho-para directing and activation influence of the OH group towards the electrophilic substitution. The ortho-para directing and activating influence of the OH group towards the electrophilic aromatic substitution can be explained in terms of assumption that oxygen of this group can share more than one pair of electrons with the ring due to the resonance. When phenol undergo electrophilic substitution, the contributing structures of intermediate carbocations formed by the attack of electrophile, say E+, at ortho, para and meta position are shown below. The carbocation formed by ortho attack is a resonance hybrid of four structures, that is 3A to 3D. Of these four structures, the 3D is particularly stable, then each atom has a complete octet of electrons. Similarly, in para attack, the carbocation is a resonance hybrid of four structures, that is 4A to 4D, in which 4D is most stable. But in case of meta attack, the carbocation is a hybrid of only three structures, that is 5A to 5C. There is no Bing structure corresponding to 3D and 4D. This means that the positive charge of the ortho and para ions is dispersed over the atoms than in that of meta ion. It is therefore apparent that the hybrid carbocation resulting from ortho and para attacks are more stable than the carbocation resulting from the meta attack or from the attack on benzene itself. Thus, substitution in phenol occurs mostly at ortho and para positions and occurs at a faster rate than in the case of benzene. The important substitution reactions of phenols are discussed below. Sixth is halogenation reaction. On treatment with halogens, phenols are very rapidly halogenated, forming the polyhalogen derivatives. For example, reaction of phenol with an aqueous solution of bromine immediately produces a ppt of tribromophenol. In fact, the reactivity of phenols towards halogenation is so great that even substituents with SO3H groups, if present in ortho and para position, get displaced. Halogenation can, however, be limited to monohalogenation stage by performing it at low temperature and in non-polar solvents such as carbon tetrachloride or at the carbon disulfide. For example, nitration. Nitration of phenols give poor yield of the expected nitro compounds. This is because phenols are the readily oxides, and nitric acid can bring about not only nitration but also oxidation of the starting phenol. For example, use of concentrated nitric acid in the above reaction leads to the formation of 2,4,6 trinitrophenol or picric acid in low yields. That next reaction is the sulfonation. Sulfonation of phenol proceeds readily to the yield either at ortho or at the para position as the main product, depending upon the temperature of the reaction. In general, low temperature favors the formation of orthoisomers, where high temperature formation of the para isomer. On heating to 373 Kelvin, orthophenol sulfonic acid changes to the thermodynamically more stable than the paraphenol sulfonic acid. That is Friedel-Crafts alkylation. Next reaction is phenol undergo Friedel-Crafts alkylation forming predominantly para isomers. The reaction is carried out in the presence of hydrogen fluoride. The next reaction is Friedel-Crafts alkylation. Phenols can also undergo Friedel-Crafts acylation to form the ortho and para hydroxy ketones by treatment with acid chlorides and acid anhydrides. But the hydroxy ketones are generally prepared by the Fries rearrangement. Gattermann synthesis. When treatment with a mixture of hydrogen cyanide and hydrogen chloride in the presence of anhydrous aluminum chloride, phenols give phenolic and aldehydes. The reaction is known as Gattermann synthesis, constitutes an important method for synthesizing phenolic and aldehydes. The aldehyde groups preferably attach at the para position. Mechanism. Gattermann's synthesis is an electrophilic aromatic substitution in which the attacking rearrangement is formaldinium ion formed from hydrogen cyanide and hydrogen chlorides in the presence of anhydrous AlCl3. Next reaction is Hoban-Host reaction. This is an acylation reaction of polyhydric phenols having hydroxy group in meta position with each other. It is carried out by treating such phenols with the alkyl cyanide and hydrogen chloride in the presence of anhydrous zinc chloride or aluminium chloride followed by the hydrolysis. Mechanism. The mechanism of the reaction is similar to Gattermann reaction and is summed up below. Special reactions of phenol. Coupling with diazonium salts. When treated with diazonium salt in weakly alkaline solution, that is pH 9 to 10, phenol undergo coupling to form the hydroxyazo compounds. Coles reaction. Next reaction is when heated with the carbon dioxide under pressure, sodium salts of phenols undergo the carboxylation to form the salt of phenol acid at orthoisomers being the main product. For example, when sodium phenoxide is heated with the carbon dioxide under pressure, the sodium salicylate is obtained as a major product. The mechanism of Coles reaction is believed to involve the electrophilic attack from carbon dioxide on the phenoxide ion as shown below. Riemann-Tiemann reaction. On reaction with the chloroform and an alkali, phenols are converted into the phenolic aldehydes. An aldehyde group being introduced onto the aromatic ring generally at the ortho position to the OH group. For example, when phenol is heated with the chloroform and aqueous sodium hydroxide, salicylic aldehyde is obtained as the main product along with the small amount of the para isomer. Mechanism. The mechanism of the reaction involves the electrophilic substitution of the phenoxide ion formed in the solution by the attack of the alkali on phenol. The attacking electrophilic rearrangement is an electron deficient dichloromethylene, that is CCl2, a carbene generated by the action of an alkali on a chloroform, or dichloromethylene is an electrically neutral but it acts as an electrophilic rearrangement as a carbon atom present in its surrounding by only 6 valence electrons. This complete mechanisms may be summed up as below. If carbon tetrachloride is used in the place of chloroform in Riemann-Tiemann reaction, phenol give rise to the phenolic acids. Next reaction is Ledder-Manesse reaction. Phenols undergo condensation with aldehydes in the presence of an acid or a base or a catalyst. The product initially formed get polymerized to form commercially important polymers. For instance, when phenol is treated with the formaldehyde in the presence of an acid or an alkali, a mixture of ortho and para hydroxybenzyl alcohols is first formed. The alcohols undergo polymerization to form a resinous polymer called the bakelite. Mechanism of initial condensation. The initial reaction between the phenol and formaldehyde involves the electrophilic attack of formaldehyde on phenoxide ion or protonated formaldehyde on phenol as summed up below. Next reaction is phthalate reaction. On reaction heating with phthalic anhydride in the presence of concentrated sulfuric acid or anhydrous zinc chloride, phenols are converted to phthalanes. For example, phenols form phenolphthalein as shown below. Phenolphthalein is used as an indicator in the acid-alkali titration. It is a colorless in acidic medium but changes to pink color in the alkaline medium. Reaction with the ferric chloride. Phenol give a violet coloration on ferric chloride due to the formation of water-soluble complex that is ferric phenoxide. Other phenols also forms colored complexes green, blue or violet on treatment with the ferric chloride. This reaction is used as an important test in the identification of phenols. This test is not given by the alcohols. Now the last reaction is Lieberman synthesis. On treatment with the sodium nitrite dissolved in the concentrated sulfuric acid, phenols give a red color. This color changes to the blue on the addition of the sodium hydroxide. This reaction is known as Lieberman's reaction. Thank you all of you. This chapter is completed.